Last time, we learned that kinematics is how we convert positions and velocities of the end effector to positions and velocities of the joints in a robot manipulator. Already, there's some terminology in that definition that might be new to you. A manipulator is another word for a robot arm. We use the term manipulator instead of arm because a manipulator doesn't always look like a human arm. A manipulator consists of a number of joints connected by links. A joint is a part of the robot that allows motion, and a link is some physically stiff component that connects one joint to another. Joints are usually powered and controlled so that the motion can be made automatically. For example, in your kit you have 5 joints, 3 RC servos, 1 stepper motor, and 1 DC motor. Let's take a look at how we can connect these joints together. First, we'll attach an RC servo to the board using the 4 standoffs like this. We're going to use these 4 holes here to attach this RC servo to the board. So first, pass a screw up through the bottom of the board. And then attach a standoff like that. And we'll do the same in these 4 holes. Now we're going to attach the servo to the top like that. For this, you can either use these same long 10mm long M3 screws, or these are also M3 screws, they're just shorter. You can use these also. I'm going to use the shorter screws. You have a screwdriver included in your kit that is the appropriate size for these M3 screws. Don't tighten the screws down until you have all 4 screws in place. So right now I'm screwing these things down, but I'm doing so lightly. They're loose. Once you have all 4 in loosely, go ahead and tighten them all down just a little bit. Don't make them too tight because you don't want to damage the plastic of the RC servo. Just enough to hold the servo nicely in place. Now, in order to attach a link to the rotor of the servo, we're going to need a piece called a servo horn. The horn is the piece that attaches to the servo gear and then can be attached to other things. There's an internal gear on this horn that matches the external gear here. So if you just wiggle it around a little bit and then push down, it will attach to the gear. And you should be able to turn it by hand. And it's a little bit hard to do because these servos have kind of a lot of torque. But you should be able to get it to turn by hand. Now, rotate this servo horn as far as it can go clockwise. The servo can only turn 180 degrees, So once you get to its stop, don't force it beyond the stop, just let it be there. Then, once it's rotated as far as it can go clockwise, pop the horn back off, and then line up the horn so that it's just a bit beyond having the two holes be straight. So line it up so that the two holes are straight horizontal, and then turn it a tiny bit more and pop it on like that. And then use the screws that came in the same container as these horns to attach the horn to the servo like this. I'm going to screw this down. Just finger tight. I'm going to put these other horns and horn screws aside. Next, find a straight link like this in your kit. We're going to attach the straight link like this to the horn. These holes in the servo horn are tapped to match with your M3 screws. So I'm going to use these little M3 screws. These are not the ones that are in the container with the servo horn. These are the ones that you have about 20 of them. And you also have nuts in the same container. Those are the screws that I'm using here. And I'm actually only going to use 2 screws to hold this on, even though I have 4 possibilities here, because 2 is plenty. And then check to make sure that this link can rotate 180 degrees. So when I try rotating mine, I see here that I've made a mistake. It's rotating between this angle and this angle, and that's not really what I want. So I'm going to try doing this again. I'm going to rotate my link all the way clockwise. And then I'll pop off the horn and put it back on so that it's not exactly horizontal, but a tiny bit below horizontal. And then I'll screw the horn back on. And now I'll test it again. I want it to be able to rotate all the way from the angle that's straight to the right and the angle that is straight to the left. So now I've got it on here like I want it to be. So we've just placed one joint on our board, and we also have 2 links. Now you might be surprised that I say we have 2 links because it looks like we only attached 1 link. But in a manipulator, a link is any stiff physical distance that exists in our manipulator. So here, 1 link goes from here to here. This is a link. We also have a link that goes from the board up to the top of this link. In other words, when we identify the links in our manipulator, we need to also take into account physical distances that come from the joints themselves. So here we have 1 joint and 2 links. Before we attach another joint to this manipulator, let's draw a picture of this 1 joint and 2 links. In robotics, we use a type of diagram known as a kinematic diagram to help us derive the equations that we will need to put into our code to control the robot. A kinematic diagram shows how all of the joints and links are connected together. Here's how we can draw this 1 joint and 2 links. The joint looks like this. This is a type of joint known as a revolute joint. A revolute joint is one that allows rotational motion of links relative to other links. This part of the drawing represents the stator of our revolute joint, and this part represents the rotor. The second link that we placed connected to the joint looks like this. I can now label the links and the joints in this diagram. I'll use the letter A to represent a link length. As I said before, we have two link lengths here, A1 and A2. I also have to label the direction of positive rotation on this joint. I have to be careful to label this direction of positive rotation so that it matches the device that we actually built. I can find the direction of positive rotation by using the right-hand rule. I take my right hand and I put my thumb in the direction of the axis of rotation of this joint. In other words, my thumb should be coming up out of the servo horn. Then, the direction that my fingers curl shows the direction of positive rotation. So, I can draw that into my diagram like this. This direction of positive rotation could also be drawn like this, and those two things would mean the same thing. However, if I drew the arrow on the other side like this, that would be wrong. It would show the positive direction being in the other direction. One way to see that this is true is to think about this picture of a cylinder that I drew as being sort of like a can of soup whose top is tilted towards you. We want to show that the positive direction of rotation is when this can of soup is rotating in the counterclockwise direction. When the can of soup rotates in the counterclockwise direction, the back of the can of soup is rotating to the left, and the front of the can of soup is rotating to the right. That's what these two arrows are showing. They're showing that either the back of the can is rotating to the left or the front of the can is rotating to the right. Okay, now let's attach a second joint to this first one. There are a number of different ways that we can do this in order to build different kinds of robot manipulators. Right now, we're going to look at a couple of those different ways, and then we're going to look at what the kinematic diagram looks like for each of these different options. It's very important to make sure that your kinematic diagram matches the thing that you built. Otherwise, the equations that you end up deriving will not be correct and the behavior of your robot will be wrong. Find one of these servo brackets from your kit. We're going to attach this bracket to the linear link like this. To do this, use one of the M3 screws, place it through the top and the bottom. I'll place a screw through the hole like that, and then through the other hole. And then I'll hold an M3 nut on the bottom while I use the screwdriver to just slightly tighten the screw. Then I'm going to do the same to this hole right there. You might have to turn the screw a bit to get it to go through the hole, but then take another nut and hold the nut on the bottom while you tighten the screw on the top. Now we're going to attach the servo to the servo bracket like that. You can either use the short M3 screws or the long ones. Hold the nut on the bottom, and it doesn't have to be very tight, just just finger tighten. I'm going to do one of the screws on the other side also, but in the interest of time, I'm only going to use 2 screws to hold this servo on. We're not going to be putting very much force on the servo, and so that will be fine. Okay, so I'll give you another view here to show you how I attach this. There we go. And I'm going to attach another link out here also. Take another servo horn and pop it on there, and then rotate it as far as it can go clockwise. And similar to how we did the last one, I'd like the holes to be vertical and horizontal here when it's all the way clockwise. So if your holes are not vertical and horizontal, just pop the horn off at this point and align it like this, and then pop it back on. Then I'll use one of these servo horn screws to attach the servo horn. Now take another linear link and we're going to attach it vertically like this. So your first joint should be able to turn between 0 and 180, and your second joint is going to be able to turn between -90 and +90. I'll be saying more in a little while about why I'm calling this angle 0 and this angle 180, but I'm calling this angle -90 and this angle +90. In other words, I have it set up so that when both angles are 0, it looks like this. When we draw our kinematic diagram, It's important to note that we're drawing the manipulator the way it looks when all of the angles are in their 0-degree position. So when I draw the kinematic diagram of this manipulator, I'm going to draw this in my picture. So let's draw this now and see what the kinematic diagram looks like. Here's what our diagram looked like before. Now I added on a second revolute joint with its axis of rotation coming into and out of the board, or towards me and away from me. Here's how I draw that kind of revolute joint. In our kinematic diagrams, we are allowed to draw lines that go left and right like this, up and down like this, and at a 45-degree angle like this. This kind of an angle means into the page, and this kind of an angle means out of the page towards us. It's a general convention that we never draw lines that are at this angle here, even though sometimes that kind of an angle means into the page and out of the page. We're not going to use that at all in robotics. Now, I still need to draw the second link that we placed on the end of this joint. So here's how I'm going to do that. There we go. Now I need to add in the labels on my link lengths. So I have a length right here. I'll call that A3. And I have a length right here. We'll call that A4. I still need to draw the direction of positive rotation of my second joint. I can find the positive direction of rotation for this second servo the same way I found it for the first servo. I put the thumb of my right hand coming out of the servo horn, and then the direction that my fingers curl shows the positive direction. In other words, when the servo rotates this way, that's positive. When it rotates this way, that's negative. I can then draw the positive direction of rotation in like this. Now, let's pause for a moment to learn some terminology. This device is called a manipulator. It consists of some links and joints connected together. This part of the manipulator at the very end is called the end effector. The end part comes from the fact that it is at the end of the manipulator, and the effector part comes from the fact that this is the part of the manipulator that does work or has an effect on things. Here is where we would put a gripper if we want to grab things, or a paint sprayer if we want to paint, or whatever kind of tool we want the robot to use. Also, we would say that this manipulator has 2 degrees of freedom, or is a 2DOF manipulator. Degrees of freedom is a term that refers to how many joints a manipulator has. We can also now figure out the workspace of our manipulator. The workspace is the area that the end effector can reach. Now, both of these joints that we have placed are revolute joints because they allow rotation at the joint. There is a second type of joint we could have placed called a prismatic joint, which allows linear motion. In order to achieve linear motion, we usually need some kind of device for converting rotational motion into linear motion. In your kit, you have a device called a rack and pinion. This piece is called the rack, and this piece is called the pinion. A rack and pinion is one common means of converting rotational motion into linear motion. let's take a look at how to build and draw manipulators that have prismatic joints by putting our rack and pinion device onto the manipulator. I'm going to start by removing this linear link from our first joint. Next, I'm going to take the third linear link that you have that we haven't used yet, and I'm going to attach the rack to it like this. For this, I'll use 2 of the long M3x10 screws. And I'll use an M3 nut on the other side. Now I'll attach this linear link to the first servo like this. This part over here is our end effector. We have one revolute joint that rotates like this, and we have one prismatic joint that moves linearly like this. When we get to the section on motion control, we'll be using the DC motor and the pinion together in order to automatically control the position of this rack and pinion. For now, we're going to take a look at how we draw the kinematic diagram for a device like this. Remember that we always need to draw our kinematic diagram to represent what the manipulator looks like when it's in its 0 position. So my first joint will be 0 when it's like this, and let's suppose that the second joint is 0 when it's like this. And this is the end effector. Let's draw this 2 degree of freedom manipulator. This manipulator starts out the same way the last one did, with a revolute joint and a link pointing off to the right. Next, we have a prismatic joint, but our prismatic joint is offset a little bit into the page. So I'm going to draw a link that shows a little bit of an offset. Now, a prismatic joint looks like a cube. And we use a square to show the direction that the prismatic joint is moving. So since this prismatic joint moves left and right, I'm going to draw the link like this. Now we have a link in the vertical direction here. We have a link in the left and right direction there. We have an offset link, and then we also have a link here. Now we need to also draw in the positive direction of rotation, and for our prismatic joint, the positive direction of displacement. So our positive direction of rotation, which we get from the right-hand rule, is like that. And since we've defined 0 as being the rack pressed all the way to the left, that means that we'll probably be defining the positive direction of motion here being to the right. And I'll use the letter D for this. I'll call this D2 because even though this is only our first displacement, it's our second joint variable. A theta for rotation motion or a D for linear motion are both referred to as joint variables collectively. Let's do one more example. I'm going to remove this prismatic joint. And I'm going to put the revolute joint back on. But instead of putting it on this way as we did before, this time I'm going to put it on at a different angle. Suppose we put the joint on at this angle instead. Now, our first joint can rotate between 0 and 180 degrees, and our second joint can rotate between -90 and +90. And its 0 position we will define like this. So since this is its 0 position, we know that to draw our kinematic diagram, we'll draw it like this. And right away, before I go draw the diagram, I'm going to make sure I know which direction is positive for the rotations. So the positive direction for the first servo is like this, and the positive direction for the second servo is also like this by the right-hand rule. So let's go draw the kinematic diagram. The first degree of freedom looks just like we had before. And there's the link. Now, when I draw my second revolute joint, this time the axis of revolution for the second joint is up, down, instead of towards us and away from us like last time. So now the second joint will be drawn like this. And there's the second link. I can label the link lengths here. And I can label the positive directions of rotation. Theta 1 and theta 2. Now, all three of the kinematic diagrams we've drawn so far are missing one super important thing: coordinate frames. In order to derive the equations that we need from a kinematic diagram, we need to have some coordinate frames on our manipulator. At a minimum, we need to have one coordinate frame that is the base frame, that is the frame that represents the world or the ground, whatever the robot is attached to. We need one frame for each joint, and we need one frame on the end effector. There are 4 rules that we need to follow when drawing these frames. If we follow these 4 rules, that will allow us later on to take a shortcut in our mathematics. It's a kind of shortcut known as the Denavit-Hartenberg method. These 4 rules that we're going to be using are not hard and fast rules. In other words, it's possible to derive the equations that we need while not following these rules. But you can't take the Denavit-Hartenberg shortcut unless you follow the 4 rules. So we're going to learn the rules as if they were hard and fast rules, so that later on we can take this shortcut. I'm going to give you these 4 rules while doing an example because I think that makes the rules make more sense. A coordinate frame consists of x, y, and z axes. Our first rule is that the z-axis has to be the axis of rotation if you have a revolute joint, and it has to be the direction of motion if you have a prismatic joint. So, in this first kinematic diagram, my first z-axis is going to be like this, and I'm going to label this axis z0. This first coordinate frame that I'm drawing serves the purpose of being my world frame or my base frame, and it also serves as being the frame that is attached to the first joint. Next, I need to put a frame on the second joint. I'm going to follow my z rule here also. So the z-axis has to be either coming out of the page as I'm drawing it here, or we could have drawn the z-axis going into the page. Either way, the z-axis rule will be followed. Now, I also need to have a coordinate frame on my end effector. But here, I can't follow the first rule because there is no axis of rotation or direction of motion because there's no joint. So if I can place the z-axis being in the same direction as the last one, I'm going to. So I'll try that initially. Z2 will be coming out of the page for my end effector frame. Okay, we've gotten through rule 1. It's time to move on to rule number 2. Rule number 2 is that the x-axis has to be perpendicular both to the z-axis of its own frame and to the z-axis of the frame before it. For my first frame, it's very easy to follow this rule because there is no frame before the 0th frame. All I have to do is make sure that the x-axis is perpendicular to the z0 axis. So I'm going to make x0 point to the right. I could have chosen to make x0 go into the page, or out of the page, or to the left, but I'm going to choose to the right. It's an arbitrary choice. Now for frame 1, my choices of which direction x can go are more limited. I can't make x come towards me or go into the page, because that would make x be parallel with z1, and I can't have that. x1 needs to be perpendicular to z1. That would mean that I could make x go to the right, to the left, up, or down. But this rule also says that the x-axis has to be perpendicular to z of the frame before it. Since z0 is up, that means I can't make x1 be up or down, because that wouldn't be perpendicular to z0. I can either make x go to the right or to the left, and those are my only options. I'm going to make x go to the right. Okay, now for the end effector frame. I can't make x come out of the page or into the page because that wouldn't be perpendicular to z2 or z1. But I can make x go to the right or the left or up or down. Anytime I make the frame and the end effector the same as the frame before it, my math is going to end up being easier. So I'm going to make x2 go to the right. Alright, we've so far followed 2 of the 4 rules. Let's move on to rule number 3. Rule number 3 is that the whole frame needs to follow the right-hand rule. I need to assign the y-axis so that the frame follows the right-hand rule. Here's how we use the right-hand rule to assign coordinate frames. I'm going to make my hand flat with my thumb sticking out like this. Then I'm going to put my fingers in the direction of the x-axis, and I'm going to put my thumb in the direction of the z-axis. then the direction that the palm of my hand is pointing is the direction that has to be the y-axis. So for the 0 frame, x is pointing to the right, z is pointing straight up. This tells me that y has to go into the page or away from me. Now let's do frame 1. Here, x1 is pointing to the right. Z is coming out towards me. This tells me that y has to be pointing up because that's the direction the palm of my hand is pointing. The 2 frame is the same as the 1 frame, so that means that y2 also has to be pointing straight up. Okay, we've now followed rule 3 also. On to rule number 4. Rule number 4 is the most tricky of the 4 rules. Rule number 4 says that each x-axis has to intersect the z-axis of the frame before it. Now, this rule doesn't apply to frame 0 since there is no frame before frame 0. Let's start by applying this rule to frame 1. If we draw a dotted line back from axis x1 and we extend z0 up, we need it to be that the dotted line extending x1 intersects with the dotted line extending z0. And in this case, it is. That means that we have followed rule number 4. Let's look at frames 1 and 2. If I draw a dotted line extending frame x2, and I draw a dotted line extending frame z1, will these 2 dotted lines intersect each other in 3-dimensional space? They will. That means that we've followed rule number 4 on frame 2 also. And so we're finished with the kinematic diagram for this manipulator. Let's do the next one. Rule number 1 is that the z-axis has to be the axis of rotation or the direction of motion for a prismatic joint. So since joint 1 is a revolute joint, z0 has to be either pointing up or down. Joint number 2 is a prismatic joint. This prismatic joint is moving to the right and to the left, so z1 needs to be either to the right or to the left. I'm going to make it go to the right. For the end effector, I don't have a joint at all. If I can make the axis the same as the frame before it, I want to do that because that will make my math easier. So here I'm going to make z2 point to the right. Alright, that's it for rule number 1. Rule number 2 is that the x-axis has to be perpendicular to its own z-axis and also perpendicular to the z-axis before it. Since frame 0 has no frames before it, I only have to make x0 be perpendicular to z0. So I could make x0 be to the right or to the left or into the page or out of the page. I'm going to make x0 be to the right. For x1, I have to make sure that x1 is perpendicular both to z1 and to z0. So I cannot make x1 be to the right or to the left, and I cannot make it be up or down. I can only make it be either into the page or out of the page. I'm going to make x1 be into the page. For the end effector frame, once again, if I can make the frame be the same as the frame before it, that's going to end up making my math easier. So x2 I'm going to make into the page just like x1 was. Now on to rule number 3. Rule number 3 is the right-hand rule. I have to draw y so that the whole frame follows the right-hand rule. For frame 0, I'm going to make x be to the right, and Z coming up. That tells me that Y is into the page because that's the direction the palm of my hand is facing. For frame 1, X is into the page and Z is pointing to the right. This tells me that the Y-axis has to be up because that's the direction the palm of my hand is facing. Since frame 2 is the same as frame 1, I know that Y2 has to be pointing up also. Now, we still need to take into account rule number 4. Rule number 4 says that each x-axis needs to intersect the z-axis that comes before it. So this doesn't apply to frame 0 because it has no frame before it, but it does apply to frame 1. If I draw a dashed line extending x1, and I draw a dashed line extending z0, it needs to be that these two lines will intersect each other. Now, at first glance, it may look like these lines intersect each other down here, but this is not true. It only looks like that because we're drawing a three-dimensional object on two-dimensional paper. In 3 dimensions, you can see that this line x1 does not intersect with the line z0. They pass by each other. So rule 4 is not followed here. In order to follow rule 4, we have to move the center of frame number 1. So far, we've consistently placed the center of each frame right at the center of each joint. That's a good practice to follow, but it's not necessarily required. We can move the center of the frame to any other location that we want. And in this case, we must move the center of frame 1 in order to obey rule number 4. The only thing we still need to figure out is which direction should we move the center of the frame and how far should we move it. Since the x1 line passes by the z0 line to the right, that means that we're going to need to move the center of frame 1 to the left. Then we need to figure out how far to move it. The x1 line passes by the z0 line right here. It passes by a distance of a2. So, in order to get the x1 line to intersect the z0 line, I need to move the center of frame 1 to the left a distance of a2. So the new center of frame 1 will be right here. I'll draw it in a different color to try and help you see it. Here's the z1 axis. Here's the x1 axis. And here's the y1 axis. The distance between the center of this frame now and the center of the joint is the distance a2. And this one frame that we drew before is no longer here. We've moved it a distance of a2 to the left. After I've done that, if we draw a dotted line backing up x1, we can see that x1 now does intersect z0. So we've followed rule 4. Next, let's check rule 4 for frame 2. If we draw a dotted line extending z1, and we draw a dotted line extending x2, we see that those two lines do in fact cross. They cross at the center of frame 2. So we've followed rule 4 for frame number 2. I know that these rules, especially rule number 4, are kind of tricky and hard to get a hold of. But the more you practice this, the more simple it will become. Let's take a look at one more example. We're going to draw the frames on our last kinematic diagram that we drew, this one here. We'll start with rule number 1. Rule number 1 is that the z-axis has to be the axis of rotation. So z0 will be up. z1 will also be up. Then, for the end effector frame, if I can make it the same as the last frame, I will. So I'm going to make z2 also be up. Next, rule number 2 says that the x-axis needs to be perpendicular to its own z-axis and also the z-axis before it. For frame 0, I could make x0 be to the right, to the left, into the page, or out of the page. I'm going to make it to the right. For frame 1, I could again make x be to the right, to the left, into the page, or out of the page. If I'm thinking ahead to rule number 4, I can see that I don't want to make x0 be into the page or out of the page, because that will make this frame violate rule number 4. I can follow rule number 4 right away just by making sure that x points either to the right or to the left. I'm going to make it point to the right. Then, for frame 2, I can make x be in the same direction as the last frame, so I'll make it go to the right also. Alright, rule number 3 is that y has to follow the right-hand rule. For frame 0, I make my fingers point to the right and my thumb point up. That tells me that y points away from me or into the page. Same with frame number 1. X points to the right and Z points up. So Y has to go away from me or into the page. And the same with frame number 2. We're already on to rule number 4. When we were drawing the x-axis, we were thinking already about rule number 4, but we should check now to make sure that we've obeyed this rule. It doesn't apply to frame 0 because there is no frame before frame 0. So we'll start with frame 1. If we draw a dotted line extending the axis x1, and we draw a dotted line extending the axis z0, do these two lines intersect in three-dimensional space? They do. They intersect right at the corner, right here. So rule number 4 has been followed for frame 1. We also have to think about whether this rule has been followed for frame number 2. If we draw a dashed line extending x2, and we draw a dashed line extending z1, do these two lines intersect in three-dimensional space? They do, right at this corner here. And so rule number 4 has been followed here also. If you'd like to see more examples of drawing frames according to the Denavit-Hartenberg rules, take a look at the supplementary videos posted in this section of the class. I'll be showing you examples of drawing frames on kinematic diagrams for the 5 standard types of manipulators. Right now, we're going to move on and do one last thing before we finish today's lesson. We've built all of these little 2 degree of freedom manipulators on our board. I'd like to show you how to get the servos moving automatically using PSOC Creator. We'll do that next.